All right, guys, we're going to look at some more modeling and curve fitting. Today we're going to focus on more real-life data. Okay, you've kind of seen all of this. Some of it will be a review. There's really only one new piece in here, and that's square root function. Looking at this slide right here, much of the data that you encounter in the real world could form a pattern. All right, and that pattern could have a special type of model, whether it be linear, quadratic, cubic, quartic, quintic, or even a square root function. You can then use the function to analyze trends and make predictions. That's what a lot of businesses hire people to do, is use these types of formulas to analyze trends. If you look at this chart, it doesn't have everything on it, but it has a lot. And one I failed to mention just a second ago was exponential. But if you'll focus down here at the bottom where it says constant differences or ratios down at the bottom of the chart, a linear. If an equation is linear, looking at a table, it will have constant first differences between y values for evenly spaced x values. So if you look at the x's and they go up by the same number, then you go to the y's and you subtract the y's, and the first time you subtract you get the same number, it's linear. For quadratic, you would do the same process, except on a quadratic, because it's x to the second power, the second differences are going to be the same. But still, the x values are evenly spaced. Exponential, that's what we did at the end of the week last week.
Teachers, excuse this interruption. Please check your email from Friday and send the students on the AccuPointer list to the conference room at this time with their Chromebooks. They need their Chromebooks and they need to report to the conference room. Thank you.
So again, exponentials, guys, would need to have a constant ratio between y values for evenly spaced x values. So if the x's go up by the same number every time, and you look at the y's and the differences aren't the same, check their ratios. That means divide. If you get the same thing every time, it's exponential. Now, a square root is when you have constant second differences for the x values. So if the x values aren't evenly spaced, but the y values are evenly spaced, go and subtract the x's, and if you get a constant on the second difference, you have a square root function. Okay, so that's the new one for today, is square root function. That's the one we haven't done yet. Remember, you're going to need your calculator. Because the square root of function is the inverse of the quadratic function, the constant differences for the x's and y's are switched. Inverse means opposite. Okay? If you had a quadratic, it's the second difference for the y's. With the square root function, which is that inverse, it's the second difference for the x values. So let's look at this first example, example 1a right here. It says identifying models by using constant differences or ratios. So the first thing you want to find out is, are there any values that go up the same or are evenly spaced? And those values, in this case, are the x's. From 5 to 10, you go up 5. From 10 to 15, you go up 5. 15 to 20, you go up 5. 20 to 25, you go up 5. Okay? So since those go up by the same number, let's check to see if the data is linear, quadratic, cubic, etc. And the way you do that is you find the first differences of the y values. Okay? So you would put in your calculator 93 minus 58, and then go 128 minus 93, and then 163 minus 128, and then 198 minus 163. And when you do that, the differences you find are all 35. And that's the first difference. Because the first differences are a constant 35, a linear model will best model the data. So that was pretty easy because the first difference fits. A lot of times, though, with what we've done lately, we've been dealing with quadratic or greater, okay, because you did linear models in Algebra 1 or coordinate algebra. All right, let's look at the next example. Again, first thing we do is look at the x values. From 4 to 8, I went up 4. 8 to 12, I went up 4. 12 to 16, I went up 4. 16 to 20, I went up 4. So the data for the x's are evenly spaced. So since I noticed that, check the first differences between the populations, which the populations are the y values. Okay, and to do that, I would subtract 9,600 minus 10,000, that's negative 400. 9,216 minus 9,600, that's negative 384. All these differences you need to be writing down. 8,847 minus 9,216 is negative 369. 8,493 minus 8,847 is negative 354. Those aren't close enough yet, so go to the second differences. All right, negative 384 minus negative 100. Now this is one you have to put in your calculator like this. I'm going to write it up here at the top of the page. Negative 384 minus negative 400. That minus negative right there actually makes this become plus 400, and that's how you get positive 16. Same thing, negative 369 minus negative 384 is 15, and then negative 355 minus negative 369 is also 15. Now, here's the thing about this one. Neither the first nor the second difference is exactly constant. The second was close, okay, but it wasn't exactly constant. So go and check your common ratios. Okay, neither the first nor second differences are constant. Check the ratios. Let's check the ratios here. So you would need to divide these numbers. Now, I know it's hard to see here, but if you go 9,600 divided by 10,000, you get 0.96. 9,216 divided by 9,600, 0.96. 8,847 divided by 9,216, 0.96. 8,493 divided by 8,847, 0.96. All of those give you roughly the same ratio. And these numbers all came from the y values, and you worked right to left, 8493 divided by 8847, etc. Okay, so since they're constant ratios, because the ratios between the values are constant, an exponential function would best model the data. So on your sheet of paper below that chart, you should write exponential function. That's what its scatter plot would look like, and it looks like it's coming down and starting to curve, kind of like an exponential does. All right, look at example 1C. Same thing. When we look at the time, that data is evenly spaced. 1 to 2 to 3 to 4 to 5. There's one in between them. So we want to check the first differences between the heights. 165 minus 132. That makes 33. 154 minus 165 is negative 11. 99 minus 154 is negative 55. 0 minus 99 is negative 99. Those differences aren't the same, so you go to the second difference. Negative 11 minus 33 is negative 44. Negative 55 minus negative 11 is negative 44. Negative 99 minus negative 55 is negative 44. So the second differences all make negative 44. This first one right here, I might have said something wrong, but it is negative 44. Negative 11 minus 33 is negative 44. So, since their second differences are the same, we have a quadratic. The first x values are evenly spaced. The second differences are the same. We have a quadratic. If you were to plot these points and look at a scatter plot, it looks a lot like a quadratic. And you can see how that graph goes up and comes over. It's an upside down U shape. Now, so on your sheet of paper, for this one, just write down quadratic. All right, when you go to the next one, it says, excuse me, this one's 1A continued. No, that's example 1A, I'm sorry. All right, so if you look at the y values this time the y values are evenly spaced. 10 to 20, that's up 10. 20 to 30 is up 10. 30 to 40 is up 10. 40 to 50 is up 10. So this is where we would be looking for a square root function. Okay, so since the values for y are evenly spaced, we want to find the differences of the x values. Okay, that's what it says here. Notice that the data for the y values are evenly spaced. Check the first differences between the x values. So here's a list of the x values. 12, 48, 108, 192, 38. All right, so on your paper, go ahead and subtract them the first time. 48 minus 12, that would be 36. 108 minus 48, that would be 60. 192 minus 108, that would be 84. 300 minus 192 would be 108. And then when you subtract them one more time, every time you subtract, 60 minus 36, 80 minus 64, 108 minus 84, 84 minus 60, I'm sorry. Every time you subtract, you get 24. So the second differences match. Now again, these are the second differences for the x values. So if you look at that chart at the beginning, it said the second differences for the x values make a square root function. Okay, so that's what this is. So on your paper, you'll want to write square root function. And you might want to write second difference of x values. So x values is a square root function. Remember, the square root function and the quadratic function are inverses of each other. If it's quadratic, the second differences of the y match. If it's square root, the second differences of the x values match. All right, example 1b. Look at the x values, 21, 22, 23, 24. The x values are evenly spaced, so there's no square root this time. I'm going to check the y values. I'm going to check their differences first. When I do the first differences, I think I get 81, 108, 144. Then when I do the second differences, I get 27 and 36. So these are not linear, quadratic, cubic, quartic, or quintic. All right, what I want to check now are my ratios. So to check my ratios, I divide this way. I take 324 and divide 243. I take 432, divide 324. I take 576 and divide 432. And when I divide those each time, I get approximately 1.33. That's what this says in the green right here. It's 1.33 on all of these. I don't know how well you can see it. So the best model here, since the ratios are constant, is an exponential model. You need to write that down. Exponential model. That's what the graph would look like. You know, it's kind of hard to tell when you plot the points if it's going to be exponential or quadratic. All right, if I drew the rest of this exponential, it would look something like that. Now, something I want you to do on your calculator so you can display the correlation coefficient, which is the letter R. You know, we've been working on those regression equations, and every time you've seen it on the board up here, it's had R and R squared, but we haven't seen it on our calculator because that mode's not turned on, but we're going to need it today. What the R value tells you is how well your data fits. If that R or R squared is really close to 1, it's probably going to be like 0.999999. If it's really close to 1, it fits better to the graph that you draw. Okay? But turn your calculator on, and you want to press second and the number 0 down at the bottom. And then you got to scroll down. All the stuff's in alphabetical order, and you're looking for this right here, diagnostic on. So scroll all the way down to where it says diagnostic on. And when you get there, you got to be careful too, because one of them's diagnostic off. The second one's diagnostic on. When you get there, hit enter, and then once it shows up on the screen, hit enter again, and it'll say done. So make sure you turn diagnostic on. If you're not sure how to do it, rewind the video and listen to what I said again. So look at example 2. Now this is an economic application. All right? And with this application, you got to understand that you're using some real life data here. Okay? So bear with me when we get to the part where I say which difference is the same, because remember, this is real life data. You want to get the stuff close. Flyers printed versus profit. Well, if you look at the number of flyers printed, which are the X values, you see that they go up by the same number each time. 100, 200, 300, 400, 500, 600. So that data is evenly spaced. What I want to do is go to the next set. That's where I would subtract from. Now, before I do that, I want to look at a scatter plot. Now, if you're going to make a scatter plot of this data, okay, you got to just sketch. All right? So, for instance, the first set of flyers is 100, and they printed 10 flyers, right? So I'm not even, I'm just guesstimating. And then, the profit was $10. And then there were 200 flyers, and the profit was $70. And then there were 300, and the profit was $175. And then there was 400, and the profit was way on up here. So you can see this thing's starting to curve and move up. It's not a straight line. It's either an exponential or a quadratic. Okay, that's the type of regression that you would be using, either exponential or quadratic. So let's look at the differences. So there's the scatter plot they drew. So let's look at the differences. So if you look here, we're looking at the Y values, which is the profit, because the X values are evenly spaced. We take 70 minus 10 and we get 60. Take 175 minus 70 and we get 105. The next one we get 137, 188, 220. And then when we go to the second differences, we get 45, 32, 51, 32. Now, these second differences are close. These two actually are identical. All right? So because the second differences are close, when the independent variables are evenly spaced, a quadratic function will best model this data. Okay? Now, if you did the division, because you didn't think that was close enough, and you went 70 divided by 10, that'd be 7. And 175 divided by 70, that'd be 2.5. 7 and 2.5 are way off. And 312 divided by 175, you'd have 1.78. So the ratio would not be constant. So it's definitely not exponential. Remember, when we looked at the scatter plot, it was either exponential or it was quadratic. So we're going to call it quadratic because the second differences are similar. They're closely spaced. So now we're going to use our calculator to perform quadratic regression. So take your calculator out, and I'm going to go real slow through the steps. Okay, the first thing you want to press is Stat, and then it's already going to have Edit highlighted, so just hit Enter. Delete out the stuff in L1, delete out the stuff in L2, and type in your data for this printing company's example. The flyers printed, the 100 through 600, that's the X. And then your profits are your Y values. So you'd start with 10, go to 70, 175, 312, 500, 720. All of those numbers go in L2. The profits go in L2. The flyers printed go in L1. Now, the next thing you would do is press Stat again. Go right one to Calc. And we said this was quadratic regression. So we'll go down to number 5, hit Enter. Go down to Calculate and hit Enter. And what you're going to see is you're going to see all of these items on your screen. Y equals ax squared plus bx plus c. It's going to tell you A is this 0.002. B is 0.007. C is negative 11.2. You're going to plug all those into this equation. And then your correlation coefficient, R squared right here, is 0.999994287, which means the data is pretty close to this line. But you could see on your scatter plot here, it's slightly off. It's not exactly on it. Okay. So what you want to write down next to this one is this function right here. A quadratic function that models the data is 0.002x squared plus 0.007x minus 11.2. The correlation R is close to 1. That means that this line's a good fit. Okay, it's a good line to use to predict future outcomes. And that's what all this is about, is predicting future outcomes. All right, let's look at the next example. It's the same thing. All right, the x values, the data in the x values goes up by the same thing each time. So we want to make a scatter plot of that data. And when you make a scatter plot, it either looks like, again, it curves either like an exponential or a quadratic. So I'm going to check the differences first, and then if they don't become constant, all right, I'm going to go back and divide. Check the ratios. First differences here, 31, 35, 39, 43, 47, and 51. The second differences are exactly the same. So in this case, because those second differences are the same, I should be doing quadratic regression. So just like in the last situation, I'm going to take the data right here from my table, and I'm going to punch it in my calculator. So I can make a regression equation, and this one's going to be quadratic. So you would go back to Stat, hit Enter, and clear out both tables, L1 and L2, and then type in your new data. Type the x values in L1, the y values in L2. Once you type in your new data, you've got everything in there. You're going to hit Stat, go over to Calc, and then go down to Quadratic Regression. Once you click on that, go down to Calculate, hit Enter, and it should bring up this page right here. For this quadratic regression, because it was perfect, remember the differences were perfect, that means that A is 0.5, B is 2.5, C is 8. And notice that it says R squared, the correlation is exactly 1. That means all of these points fit on the line. That's why the points here, guys, are filled in. The line's rolling right through them. On the example before, let's see here. On this example before, these dots are empty on the inside. They're not exactly on the line. But on our example here, because the second differences were all 4, not close to 4, all 4, every piece fits on the line. So my model that you want to write down is 0.5x squared plus 2.5x plus 8. That is your quadratic model. It comes from this information right up here. A is 0.5, put it where A is. B is 2.5, put it where B is. C is 8, put it where C is. Now, when data are not evenly spaced or ordered, you might have to try several models to determine which best approximates the data. As you're trying several models, meaning you might have to try cubic regression, quadratic regression, and exponential regression on the same problem. To figure out which one to use, you look at the correlation coefficient, r squared. The closer it is to 1, the better the model approximates the data. Okay, so let's look at application number 3. All right, this data shows the population of a small town since 1990. So let's stop right there. That's going to be year 0. 93 would be 3 years later. 97 would be 7. 2000 would be 10 years later. 2002 would be 12. 15, 16. Those are the numbers you're going to use for your x values because the years are x's. All right? So none of the data are evenly spaced. So you can't analyze differences or ratios. Since the years go up by 3, 4, 3, 2, 3, 1, it's not evenly spaced. None of the y's are evenly spaced. You can't do differences or ratios. What you need to do is make a scatter plot. Okay, and that's just sketch it on your sheet of paper and see what the shape looks like. Okay, and if you're going to make this scatter plot, make 1990 year 0. So at 0, let's see, this goes from 400 to 1100. So I'd put 500, 1,000, and then 1,500. That would be my scale for my y's. So 0, 400. Let's see, 1, 2, 3, 490, 4, 5, 6, 7, 642 would be somewhere in here, 8, 9, 10, 787, be up above that just a little bit. This one's probably actually down just a touch. 11, 12 would be 901, 13, 14, 15, that's 1100, this is up in here. And then 16 would be just right above that one. Okay, so if you were to connect through these, it does have a little curvature in it. Also, right up here, it could have that little curvature of a cubic. So for this one, and I'll show you a different picture here. But for this one, it could be quadratic, cubic, or exponential. If you look at how these dots show up, right here, where it kind of flattens right there, that's where they're saying it's cubic, because remember, a cubic looks something like that. Okay, so we're going to have to try all 3 of these with our data. So we're going to have to make regression 3 times. All right, so we'd go back to the page before, and we would type the x values 0, 3, 7, 10, 12, 15, 16, and then the y values would be 400, 490, 642, 787, 901, 1104, 1181. And to do that, you only have to type the data in once. You just have to do the regression 3 different times. So to type the data in, you would hit stat, hit enter, type in the 0, etc. for the x's, and then type in those y values for L2. And remember, we said we need to do cubic, quadratic, and exponential regression. The biggest thing that we need to know is what's the r squared value, the correlation coefficient. So once you punch all that data in, let's just start with cubic. You hit stat, go over to calc, and go down to number 6, which is cubic regression. Hit enter, go down to calculate, hit enter. Write down that equation and write down the r squared value. Write down the whole r squared value because you're going to have to compare them all. After you finish that one, hit stat again, go over to calc again, and go down to quadratic regression. Go down to calculate. Write that equation down. So for cubic, you probably had something like y equals 0.04 x to the third plus 0.77 x squared plus 27.4x plus 399.9. And that was your cubic, and the r squared there was 0.9, let's see, 1, 2, 3, 4, 5, 6 nines. Six, 5, 7, 8. Okay, so that's what you would write down. You'd write that down for each one. One for cubic, one for quadratic, and one for exponential. All right. Now, once you do that, you then have to make a decision. Which one fits best? So I'm going to show you the three screens right here. There's quadratic, there's cubic, and there is exponential. All right. If you look at their r squared values, quadratic, it goes 0.999. Only got 3 nines. Cubic goes 0.999999. It's got 6 of them. Exponential goes 0.999999 with an 8. So 1, 2, 3, 4, 5, 6. This one has 6, but when you look behind it, it's got 8. This one has 6, but it only has 6 behind it. So exponential regression is the one that fits the best because this number is closest to 1. So exponential regression would be the correct answer. So you would write down 99.94 times 1.07, because that's b to the power of x. That would be your answer, because exponential fits it best. Again, we didn't subtract. So if you look at the next example, the x's go up by 3, then by 11, then by 6, then by 9. So there's no pattern there. There's no pattern at the bottom. So we're going to have to make a scatter plot. Okay? On these, when you make a scatter plot, it's either quadratic, cubic, or exponential. Same thing. Here it comes, kind of flattens out. Okay, so it's one of those three. So again, go back to this data right here. Type the top line in for L1, the bottom line in for L2, and then find a cubic regression, a quadratic regression, and an exponential regression, and compare their r squared values. When you look at the three types here, and you look at the r squareds, this one has 1, 2, 3, 4, 5, 6. That one's got 6 nines. This one has 1, 2, 3, 4, 5, 6 nines. And let's see, r squared, this one only has 1 9. Okay, so exponential's out. All right, this one has 6 with 8, 3 behind it. This one has 6 with 8, 3 behind it. So we're still good there. This one has 0. This one has 6. So it's going to be cubic regression because the r squared value is closest to 1. So the answer you need is negative 9.3x cubed minus 0.2x squared plus 23.97x plus 5.46. Again, all these numbers right here came from right there. And again, they rounded. Negative 9.27 is negative 9.3. Negative 0.19 is negative 0.2. 23.968 can be 23.97. And then 5.458, 5.46. Okay. So some of them you have to figure out what type of regression to use, and you do that by doing the regression for all of them and looking at the r squared value. Whichever one's closest to 1, that's the one you use. All right, that's all I have for you.